In this part we are talking about audio analysis using Audacity and about additive synthesis. Now, in the interactive teaching session, we've done just that. We've done audio analysis using Audacity and created an additive synthesizer using SuperCollier. Now, additive synthesis is based on the idea that a timbre can be generated by just adding up sine waves. These sine waves have to have a certain frequency and a certain amplitude, and by adding them up, a new timbre is going to generate it. And this is based on the so-called Fourier theory, which postulates that a sound consists of a fundamental frequency and a set of partials, which could either be harmonic or inharmonic, and these partials are also called overtones. So basically, all we have to do, we have to create a number of sine oscillators and just add them up. Okay, now what we've tried to do is we took recordings of real instruments and tried to analyze them in order to see what partials they have. So in order to analyze that, we used Audacity. So Audacity is a powerful audio editor, and it's also an analysis tool, and what you can do with it is you can record, import and export sound. You may edit it, you select sound, you have effects, you even have got real-time effects, you've got generators, and you've got analysis functionality. It enables you to multi-track record and playback, and the tracks could be audio tracks and MIDI tracks and label tracks and also time tracks. And with the new version 3.4 there are also some new musical features like grids and stuff like that. So very powerful tool. You can download it for free, it's open source. And what we see here is a multi-view of a flute signal. It's just a recorder, so C-Flöte in German, a recorder, and I've played a simple melody here, and up here you can see that the Audacity is displaying the time signal, namely the oscillogram, and below I just put the spectrum view so you can see the frequencies that are part of the signal. Alright, now in order to analyze this signal, we need to select a stable part of the signal, which is at least by visual inspection seems to be of the same volume. Then we press Z in order to position the boundaries of the selection on a zero crossing of the signal, so we've got a clean start and end. And then from the analysis menu we simply select plot spectrum, and with this we get the spectrums. Now the spectrum is a frequency analysis, and it simply says which frequencies are part of the signal. I'm sorry, I've got a coughing here, but I can't help it. So as you can see, we have a set of frequencies and a set of spikes, and these spikes basically represent the partials, the overtones. All right, and as you can see, the red line here is positioned on a frequency of 880 Hertz. The system has a snapping mechanism, so once you move the mouse over the spectrum, it will snap to certain values, the highest values. And as you can see, I've played an A5, and then there's here, 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 and here, and so on. There are spikes, and these are the overtones. These are the partials. So we can see we've got the fundamental, and then we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 partials, or even more probably. And then there's some noise, which is obviously the part of the signal, as for example the recorder is a wind instrument, so you blow into it, so you've got some hissing and these kind of sounds, and they will be represented here. But for the pure tone that we hear, we simply have these overtones with a certain amplitude. All right, so this is kind of like the signature, the fingerprint of the flute. Now in order to work with this data, we may export the data. As you can see here, we are exporting it, and what we are getting is basically just a list of frequencies and volumes. So each frequency is denoted with a certain volume. So the volume, the amplitude, is specified in decibels, so we have to translate it into a factor, which can be done quite easily using SuperCollier. Now, working with the data, obviously, and this is a table kind of like structure, and just importing it into Excel or LibreOffice Calc, which I'm using, helps. You may sort according to the frequency, you may sort according to the level, and so on, and then you can search the list quite easily. So once you've got that, you can turn that into a synth, an additive synth, and here's the code for that. We basically have got a number of variables which are denoting the frequencies, and as you can see, for each of the frequency, the fundamental frequency, and each of the partials, I'm just starting a sine OSC, and as you can see, I'm using the frequency and just multiply it by 1 to 14. So these are harmonic partials. And for the volume, I'm using the values which I've recorded using Audacity. And as you can see, here are the amplitudes for the partials. And in order to get a factor, because for multiplication we need a factor between 0 and 1, we are using the function dBamp, which is transcoding the value from dB to amplitude. All right, and in order to make the sound a little bit more vivid, I also implemented frequency modulation and amplitude modulation. So I'm just using two sine oscillators again with a very low frequency, and as you can see, I'm just varying the values between 0.995 and 1.005. So just a very subtle change, and the first modulator is going to be used for the frequency, so it's multiplied here, and the second one is going to be used for the amplitude. And as they have got different frequencies, I get a little bit of movement within the sound. It's not very spectacular, but okay. And then again, I also added some noise. I used some pink noise, and as you can see, I used the bandpass filter, which is centered around the frequency, the fundamental frequency, and we've got a certain RQ value, and as you can see, the pink noise is relatively soft. It has only got 0.1 amplitude. So in order to create the sound, we are just adding up all the fundamentals here, and then we are adding the noise, and then we are also using an amplitude here, and with pen 2 we are centering it in the middle, so we've got stereo signal which is centered in the middle. Now there's one more thing here, which is the envelope. Now the envelope is simply there to control the volume over time, so basically how the sound starts and how it fades away. And I've chosen to use an ADSR envelope. On the next slide you can see its behavior. So basically it just goes up very fast and has a little bit of decay, then it stays on the sustain, which you can't see here on the plot, and then it goes fades away in a second or so. Actually it's not that realistic, but I wanted to have a little bit of kind of like meat in the sounds to really analyze it. So the ADSR has a attack time of 0.1, then a decay time of 2, then a sustain level of 0.7, and a release of 0.1. And with these parameters, I'm starting the envelope generator, and as you can see, it gets the params. The gate is going to be taken from the parameters here of the synth. The 1 is the multiplication, so it's as loud as it should be, and we've got the done action 2, which we always have. As soon as the gate is going to be set to 0, the envelope generator is going to finish, and then the surrounding synth def is going to be released. So we are releasing the stuff. So very standard approach we're using in SuperCollier, and this can then be used to generate sound. Okay, I also implemented two more variants of it, and the second one I'm just going to show to you. The second variant, instead of creating 13 sine OSCs by hand, I simply used multi-channel expansion. So as you can see, I'm just giving an array of the frequencies. Frequency 0 is going to be set to frequency, so F0 is the frequency, so I just multiply it by 1, 2, 3, 4, 5 and so on in order to get harmonic partials. And then in order to to get this movement into the frequencies, I just have to multiply it by the modulator. And as you know, the multi-channel expansion is going to create 13 channels or 14 channels here, and with these 14 channels, no, with these 13 channels, excuse me, each of which has a different frequency. Now, the same is to be done for the multiplications, for the amplitude. So here I'm using the values that I measured with Audacity, and in order to convert it to amplitude, I just add the dB amp, and again I'm using the modulation one to modulate the amplitude. And that's it. But if I have multi-channel expansion, I usually would have 13 channels, which I don't want. So I'm using the mix UGen to mix it all down into one signal. So I think this is a little bit more readable and a little bit more understandable, specifically because you actually don't need the first line or need to understand the first line, apart from the fact that it's the number of partials that you can see here, and you just have to copy these amplitude values from the Audacity part. And then I'm using pan 2, and this time I'm just adding the noise to the signal 1, and the rest stays the same. Now, the final thing I didn't really implement, at least not today, but I used it before in other examples, because additive synthesis, in the way that we've seen, is also a part of SuperCollier library, and there's one UGen which is called Dünklang, and Dünklang is a dynamic sine oscillator bank, and so just as we've seen before, we simply specify the frequencies and the amplitudes in an array reference, and then Dünklang does all the rest for us. It mixes everything up and scales it and stuff like that. Alright, so have a look at the documentation and try it out. It's not very complex. Alright, let's listen to a recording of our synthesizer. I just played a little melody. Let's have a look. So here it comes. Yeah, fantastic. And of course, what I've done is I've just added MIDI support for the synthesizer, which makes it far easier to experiment a little bit with it. All right. Okay. Conclusions. So, additive synthesis builds the sound from a weighted sum of sine tones. So, in principle, with this approach, every periodic signal could be generated, and so we basically may end our synthesis theory here, because we basically have a theory that enables us to create any possible sound. Now, the problem is that it may recreate a periodic signal, but the sound from a musical standpoint is very static. So nothing is moving, nothing is changing over time, and so despite of the timbre, the fact that the timbre is quite okay, it's not very musical. So what you can do, and as I've shown here, modulating frequency and amplitudes helps a little bit and makes the sound a little bit more vivid. Also adding noise could enhance the sound, but still sometimes it does feel a little bit, cold and machine-like. So we probably might have a look at some more approaches how to do synthesis. Okay, so that's it for teaching a 1 audio analysis using Audacity and additive synthesis.